You know, it's easy to forget, but we're surrounded by these invisible computers that pretty much run our entire world. And I'm not just talking about your laptop or your phone. They are literally everywhere, silently running the show, in your watch, your car, even the hospital equipment that keeps us safe and healthy.
Think about it. It's right there on your wrist, in your watch, a tiny little computer tracking every step you take, every beat of your heart.
It's in your car, right? Managing the engine, making sure the airbags go off in a split second, and of course, guiding you where you need to go. And yeah, it's in our hospitals, keeping pacemakers ticking away, making sure diagnostic machines are spot on. These things aren't just gadgets, you know? They are the absolute invisible backbone of our modern lives. So, that begs the question, right? Who are the people who actually build this stuff? Who are the master architects of this embedded world? The ones who build that critical bridge between the physical hardware, the chips and circuits, and the abstract software, the code that makes it all work. Well, to figure that out, we've got to take a little trip back in time. To find the answer, we have to go back to the years right after World War II. Now, computing as we know it was just kicking off, but it was totally split into two very different worlds, and they were facing one huge problem. They just didn't speak the same language.
And the seeds of a solution really started to sprout at the University of Michigan. It kicked off in 1946 when Arthur Burks, who was one of the co-creators of the legendary ENIAC computer, he joins the faculty. By 1953, the university has its very own digital computer, MIDAC, for defense research. Then, in 1955, a mathematician named Bernard Galler starts teaching computation courses. And boom, by 1957, a formal graduate program called Communication Sciences is officially born to study these new systems.
Okay, this slide right here, this is what nails the core problem. On one side, you had the electrical engineers. Let's call them the masters of the body. They were the ones building the physical machines, the circuits, the tubes, all the hardware. And on the other side, you had the mathematicians, the masters of the mind. They were writing the abstract instructions, the logic, the programs. But there was this massive gap between them. To really make progress, you needed people who could understand both sides, the machine itself and the logic that ran it.
And this quote just brilliantly shows how revolutionary the idea at Michigan really was. See, they weren't just trying to train people to build better computers. No. They wanted to understand information itself, whether it was processed by a machine or a human brain or even a biological system. It was all about the fundamental principles of communication.
So this wasn't just some new department. This was the birth of a totally new way of thinking. It was a deliberate mashing together of different fields, all designed to create a new kind of problem solver, someone who could finally bridge that gap between the machine's body and its mind.
I mean, just look at this curriculum. For the 1950s, this is incredible. They were combining electrical engineering with math and logic, sure, but they also threw in linguistics, psychology, and even the study of biological and social systems. The whole point was to create graduates who could think about information in a completely holistic way.
And you can actually see how this program's identity evolved over the years. It starts out as Communication Sciences back in '57. About a decade later, it gets renamed to Computer and Communication Sciences, a little more on the nose. And then finally, in 1984, it merges into the College of Engineering. And that's when we get the modern electrical engineering and computer science department we see today. That really solidified the identity of this brand new field.
And the impact was immediate. I mean, the program's very first PhD graduate, a guy named John Holland, went on to pioneer genetic algorithms, a concept inspired by biological evolution that is absolutely central to AI today. It's just a perfect example of how powerful this new interdisciplinary approach was.
So, after all that history, what has this field actually become? What exactly is computer engineering today? Well, it's all about being the master of both hardware and software.
Here is the modern definition for you. Computer engineering is the discipline that formally brings together computer science and electrical engineering. These are the folks who design, build, and maintain both the physical parts and the coded instructions for basically everything, from a massive supercomputer all the way down to the tiny chip in your toaster. You could say they're the ultimate hardware-software translators.
And the stuff they work on spans an absolutely incredible range of fields. We're talking designing microchips, building the embedded systems in robots and drones, creating the networks that run the internet, developing artificial intelligence, even managing huge power grids. It's everywhere. Which brings us right back to today. We are now living in a world that is completely, 100% dependent on the work of computer engineers. But as we've all learned the hard way, with that kind of power comes an immense responsibility.
And the demand for these skills, it's enormous. The top career paths are things like software developers, computer hardware engineers, and information security analysts, all jobs that are just fundamental to our economy and, frankly, our daily lives.
But what happens when that bridge, that critical link between the physical machine and its instructions, what happens when it fails, when it breaks down? Well, the consequences can be catastrophic.
Let's just look at a few stark examples. For the Boeing 737 MAX, flaws in the software of an embedded control system directly contributed to the deaths of 346 people. Back in 2015, a vulnerability in a Jeep's infotainment system, the radio, allowed hackers to remotely take control of the vehicle, which led to a recall of 1.4 million cars. And in 2018, an Uber self-driving car's perception system misclassified a pedestrian, which resulted in a fatal accident. These aren't just simple bugs, these are failures at the very core of computer engineering.
And all of these events really highlight the huge ethical imperative facing the field today. It's just not enough to make things work anymore. Now it's about ensuring safety and reliability, protecting our security and our privacy, demanding transparency and accountability in the systems we build, and providing long-term support so these critical devices don't just become insecure or useless.
And this isn't some fringe idea, you know? As the National Academies of Sciences, Engineering, and Medicine put it, addressing these ethical challenges is vital. It's a core responsibility for the entire computing community, from the top researchers all the way down to the engineers building the products we use every single day.
So, from its humble origins trying to connect two separate worlds of thought, computer engineering has literally built the world we now all live in. The discipline that was created to bridge that gap between hardware and software now faces its greatest challenge yet, making sure that bridge is strong enough, safe enough, and ethical enough for all of us to cross.